Hello and welcome back to another episode of Math with Son. Today we're going to be talking about two-dimensional kinematics launching from an angle, and this is going to be part one of like 3. So let's get into it. If we have it launched at an angle, it is important to recognize that the x component and the y component are still going to be considered and done separately. So if they're still considered and done separately, we would need to recognize that this is just a right triangle in a way where your opposite relates to the y component, and opposite over a hypotenuse is sine, and adjacent would relate to the x component, and adjacent over hypotenuse according to trigonometry would be cosine. And if you solve for that, you would find out that the x component for velocity would equal the initial velocity at that angle times cosine of the angle, or cosine theta. And for the y department, it would be v times sine of the angle, and that would separate whatever this initial jolt out is into a y component and an x component for vertical and horizontal for us. Now, at any given point, that's just at the very beginning. At the very beginning, it's v cosine theta, okay? And v sine theta for the y component. But at the very end, or at any given moment, at any time after that, there's some other forces that would be affected for it. Now for us, for AP Physics 1, that the vertical component will change, but the horizontal component won't, for at least right now. We're not going to deal with friction, so it is going to continue horizontally until it hits the ground. And when it hits the ground, it just splats, it's done. All right, it doesn't roll any further. So v cosine theta will remain constant the entire time, but the vertical component will be affected by gravity, and gravity will be using the formula v equals v0 plus at, that kinematic equation, which means that vy, I didn't leave myself enough space, would be vo, which is the original part, v sine theta, plus gravity, which would be negative 9.8 times t. Because gravity will influence the vertical component, it will not influence the horizontal component. It will continue shooting horizontally. Whatever it started with will be what it ends with. Let's do an example. All right. Find the vertical and horizontal components of the initial velocity for a cannonball that is launched 30 degrees and has a velocity of 60 meters per second. So what that means is that there's this cannonball being launched this way at 30 degrees, and that is 60 meters per second. We need to figure out the vertical and horizontal component just using basic SOHCAHTOA stuff. So opposite, adjacent, the horizontal component will be the adjacent and will involve cosine, and utilizing the formulas we just did up here, which is basically just doing SOHCAHTOA, with the hypotenuse on the bottom, you multiply, so the horizontal will be 60 times cosine of 30, and 60 times cosine of 30 is 60 cosine of 30, 51.96 meters per second. And the vertical component will be the same thing, but with sine. It'd be 60 times sine of 30, which ends up being, I believe, 30 meters per second. Let's find out. 60 sine 30 is 30. 30 meters per second, because sine of 30 degrees is 1/2. How long after being launched will the cannonball hit the ground? Well, that depends on where it is launched, which is going to segue us into the next video as well. For this example, it is being launched from the ground. If you don't have it being launched from the ground, it will change how the problem will be done. So this example for today, we're being launched from the ground, so we want to know when will it hit the ground again. Okay, so we essentially want the change in y to equal 0. Okay, so we want it to start on the ground and then land on the ground, so the height, although it has changed numerous times, has reached 0. Interestingly enough, here, the maximum height would be when your velocity final is equal to 0 for y, the velocity final for y, because at this moment it is neither going up nor down. Okay, so if you needed to find when it reaches its maximum height, velocity final for y would equal 0 meters per second. Not the question at all. It wants to know how long after the being launched will it hit the ground. Well, let's use our kinematic formulas. We know that we want it to be the change of y is equal to 0, and that would be v sub 0 t plus 1/2 at squared. And a would be needed because it is the vertical component that would determine when it hits the ground, not the horizontal one. Your initial velocity, we found out already, was 30 in the vertical department. So 30t plus 1/2 times negative 9.8. Probably should just simplify it and use 10, but that's okay. T squared, we want that to equal 0. All right? So with that in mind, you got 0 equals 30t plus negative 4.9t squared. You can either use the quadratic formula, graph, or factor in this case. You could factor out a t, and you'd be left with 30 minus 4.9t. And if we do the solving for that, you get a time of 0, which makes sense. It was on the ground at t equals 0. And then when does it land? Well, that would be when you set 30 minus 4.9t equal to 0. And if we solve that, negative 30 divided by negative 4.9 is, drum roll, a time of 6.122 seconds. Bueno. And also done with part B. Part C. How far away will the cannonball land? So I'm going to rewrite the time because I'm probably going to need that. 6.122. 6.122. Yep. Okay, that is when it landed, how long it took to land. Well, in order to figure out how far away the cannonball traveled, we would need to figure out the x component of that. And the x component is dictated by the horizontal meters per second. Well, we found out the initial horizontal was 51.96, and there is nothing affecting that. The entire journey, it is traveling at 51.96 meters per second. That never changes. It goes up, it goes down, but it's continuing to move to the right at 51.96, negating air resistance. So how far will it travel if it's going 51.96 for 6.122 seconds? Well, you would just multiply those. You could also reference your kinematic equations again, but really all you're going to be doing is multiplying those, and you would end up with, when you multiply them, a 318.09 meter distance of travel. That moved a lot. Well, it was cannonball. All right. How would increasing the launch angle affect the time that the projectile is in the air? And this is an important one. If you increase the angle, so let's say we started with an angle right here that's really narrow, and then we move it to an angle that's about 45 degrees, and then we move it to an angle that's bigger than 45 degrees, like 60 degrees, and then we move it to an angle that is perfectly 90 degrees, okay? The angle that you have is dictated with how far it will go and how long it will be in the air. The closer you get to 90, if you take all of your energy and put it in the vertical direction, that means that every bit of the energy will be like put into keeping this thing in the air. It's not going to go to the left or the right, which means all of it's going to go up. And if all of it goes up, that means this will stay in the air the longest. Okay? Stay in there the longest. So if we increase the angle, it will stay in the air longer and longer and longer. All right? Now, interestingly enough, that this 45 degree will make it go the furthest. And every moment after that, it would be either decreasing in length and or increasing in time. But 45 degrees is the perfect butter zone for going the furthest, and 90 degrees is the longest it will stay in the air. All right? That's going to do it for this one. Until next time, everybody, stay positive. I will see y'all in the next one when we deal with an object being launched from a given height. All right? Stay positive. See you then. Bye.